Hi, in this video we're going to have a small example. We're going to show a small example about how to calculate my RC circuit when I have sinusoidal input of a particular frequency. So in this case, we're going to have our input voltage is going to be 5 sine of 1000 t. Our resistance is going to be 1 kilo ohm, and our capacitor is going to be 1 microfarad. So we have a circuit with a capacitor there. So we know immediately that we need the impedance of the capacitor. And we have a sine wave here, so we also need to put all our elements or quantities in phasor representation. So first, our input voltage in phasor representation is 5 with an angle of 0 degrees, because I don't have any phase here. And the impedance of my capacitor is minus J over omega C, which in this case is going to be minus 1J kilo ohms. And this, in phasor representation, is the magnitude, which is 1, with a phase of minus 90 degrees, like we saw in the last video, kilo ohms. And the impedance of our resistance is simply 1 kilo ohm, because it's a normal resistance and its impedance is real. So it's just that number. So if we have all these, so the phasor representation of this is 1 at 0 degrees kilo. Sorry, there's a 1, yeah, that's the J. Yeah, so the nice thing about working with impedances and phasors is the following. Impedances and resistances behave in the same way. So when I have two impedances connected in series, like in this case, the total impedance of the circuit is the sum of in series. The total impedance of the circuit is the sum of the impedances. And when they're connected in parallel, so we also have, like in the case of the resistances, if they were connected in parallel, we would have this situation. And another very nice thing about working with impedances and phasors is that we can simply use the same rules and analysis methods we know already, like Ohm's law and Kirchhoff's law, to analyze our circuit, with the only difference that we're dealing with complex numbers now and not only real numbers. So for instance, in this case, if I want to calculate my output voltage and I have this circuit, I can just apply the voltage divider rule that we know already. So that my output voltage would be my input voltage times the impedance of my capacitor over the sum of my impedances, of my two impedances. And then we just plug in the numbers in their phasor representation form, and I have 5 at 0 degrees, volts times 1 at minus 90 degrees kilo ohms. That's my phasor representation of my capacitor's impedance over the sum of both. In this case, we're going to put 1, or let's put it like this. 1 plus 1 minus 1J kilo. It's my capacitor and my resistor added together. Yeah. So now I would like to put this one in phasor form so that we can do this division here. So I have 5 at 0 degrees volts times 1 at minus 90 degrees kilo ohms. And here, in order to calculate the phasor form like we saw in one of the previous videos, we need to calculate the magnitude and the phase of these two, of this complex number. So the magnitude is 1 squared plus 1 squared and square root of that. So it gives me square root of 2. And the phase is the minus 1 over 1, the inverse tangent of that, and that gives me minus 45 degrees kilo ohms. So now this one goes away with this one, and we're left only with volts, which is a good thing because that's what we're calculating here. And now what we do, how we do this division is we divide the magnitudes and we subtract the phases. So the output voltage is 5 over square root of 2 with a phase of minus 90 plus 45, because minus 90 minus minus 45 is minus 90 plus 45, with a phase of minus 45 degrees. And 5 over square root of 2 is approximately 3.5 volts, so volts here. With a phase of minus 45 degrees. And that is our result. Now, when we reach this point, we have to remember that we had also a frequency of 1000 radians per second. Yeah? So we need to bring that back. So what we would do is very carefully, it's not an easy task, I must say. Let's say if I had my input voltage which looked like this, and that would be my 1000 radians per second. Yeah. Sorry, I have here time and voltage. And my output voltage would be 3.5, let's say that this was, 5 volts here. And if we have 3.5 volts, so that would 2.5, 3. That would be, let's say, somewhere around here. I have 3.5 volts. And somewhere around here, minus 3.5 volts. My output voltage would be 3.5 volts in amplitude with the same frequency, but minus 45 degrees shifted. So it will look more or less like this, and then this is where I get problems. Because I have here this. So I start from here to here, and then back up again. Sorry, too far. So it would look more or less like this. So I'm back here. So it's got a smaller amplitude, which is 3.5 volts here. It's got the same frequency, or it should have the same frequency somehow. It doesn't really look that way. Wait a minute, this was here, I believe. Yeah, it's got the same frequency, and it's just shifted minus 45 degrees like this. And that is how our voltage would look like. So, in the next video, we will talk about what we call frequency response of this circuit, which is basically what happens when my input signal has got many frequencies, or like, for instance, a frequency sweep. How the circuit would react, how would the amplitudes and phases would look like. So that's it, and thanks for watching.